So we'll continue with the chapter 6 review. Last time we went over the two types of energy, kinetic and potential energy. We changed calories into kilojoules, so which are regular unit conversions calculations. Then we used the, and let me share this. So in the reference packet, chapter 6 is on the first page to the left, upper left corner of the first page of the reference, has, things you need for chapter 6. And like here, the table in green that gives the kilocalories per gram of carbohydrate or fat or protein, or kilojoules per gram of carbohydrate, fat or protein. So we can use these as conversion factors. And so today we'll use the equilibrium constant, which is below that, the equilibrium constant. That's a topic of chapter 6. And so, we learned to recognize exothermic and endothermic reactions given the enthalpy change or the heat of reaction, which is the delta H value. So when delta H is negative, you have an exothermic reactions, which means heat released to the outside. Products are lower in energy, and that means they are more stable and have stronger bonds. So in chemistry, whenever you have a stronger molecule with a more stable molecule, it will have a lower amount of energy. And we learned that this delta H value is given for a chemical equation that shows how reactant and product are reacting and being produced, and those proportions, the enthalpy of reaction gives the energy value per molecule, per mole that react according to those proportions given in the chemical equation. And then the energy diagram, you want to be able to draw an energy diagram, and they are different if you have an exothermic reaction or an endothermic reaction. And this one shows an exothermic reaction because you see that the delta H, which is the label 4 here, is enthalpy of product minus enthalpy of reactant, and it would be a negative value here, so it's a exothermic reaction. And then the difference between the energy of the reactant and the transition state here is the energy of activation, and that's what determines the rate of the reaction, which means the speed of the reaction. And you can increase the speed of the reaction by adding a catalyst, increasing the temperature, or increasing the concentrations of reactant. And so we were arrived there, where we are now ready to write the equilibrium constant expression for the following chemical equilibrium. So when you need to write an equilibrium constant expression, you need to be given a chemical equation, a balanced chemical equation. And so we saw, and let's look at it again quickly. We saw that the equilibrium constant has this expression, you see here in the middle left here of the screen. Kc, which is the equilibrium constant in units of concentrations, because there are equilibrium constant that can be in pressure of gas or volumes. Sometimes they can be expressed in different variables, but this one is by concentrations. And so it's the concentration of the product over the concentration of the reactant. And so you take the product and you will use their coefficient in the chemical equation. Those coefficients will become exponent for the corresponding concentration. And you multiply those two together, and the denominators, they are multiplied together as well. So let's take that formula and apply it in the example we have. So insert. It's okay. The little c is not necessary because we will only see this kind of equilibrium constant written in units of concentration. So it's the concentration of products, and I guess I'll rewrite that, products over the concentration of reactant. So this is really simplified because you also need exponent when you have coefficients other than 1. So here our products are, so products are on the right side of the arrow, right? So here we have PBO. So when you write the equilibrium constant, you have to pay attention to the physical state. And here PBO is a solid. And whenever you have a solid or a liquid, we do not include them in the equilibrium constant. I know that it's easy to forget, but yeah, we don't include them because they are considered to have a constant concentration. And so basically they will be, you know, included in that constant value. So then we don't, you know, put them into the expression. So PBO will not be included in this equilibrium constant. We have SO2 here. It's a gas, and gases are included. So it's solids and liquids that are not included. Gases and aqueous solution would be included. So let me put this in a subscript, sorry. So concentration of SO2. And we said that the coefficients that are in front of the formula in the chemical equation will become exponent for that concentration. So here, actually, I have to take all of this and make it a superscript here of 2. And that 2 here, that is the exponent here, comes from the 2 that was in front of SO2. So the coefficient becomes an exponent for the given formula. So in the numerator, that's the only thing we will have because the other product is a solid. So now in the denominator, we have, oh, PBS, it's also a solid. So PBS will not be included in the equilibrium constant either. So only O2 here. O2, concentration of O2, the gas, because it's a gas, so it's included in the equilibrium constant. And here it will have an exponent of 3, because there is a 3 in front of O2, right? So that exponent 3 comes from that coefficient 3 in front of O2. And that's it. That's the equilibrium constant for this equilibrium. So what you need to remember is solids and liquids are not included. It's product over reactant, and you use the coefficient as exponent. And when you will calculate a value, there will be no units, because you see the numerator and denominator can be so different and never the same. So that's why K has no units. Even though these are concentrations in molarities, you end up with no units for K. So let me put that in blue so we see. Okay, so that's it. When you need to write the equilibrium constant expression, that's what you need to do. And here it's actually using the same equation here. It's asking you to calculate the equilibrium constant value if the concentration at equilibrium are O2 0.020 molar, SO2 0.60 molar. So you want to, and so I guess I can copy that thing, this whole thing, copy, and we will continue. And now plug in the values because we are given the concentration at equilibrium, right? It's the concentration when you have reached the equilibrium. And for SO2, it's 0.60 squared, uh, squared. And on the bottom, it's 0.020. That's the concentration of oxygen. And this is cubed. So in your calculator, you do 0.60 squared. You know, you have a key for that probably in your calculator, divided by 0.020. And then you do the caret key, 3, to say, raise that to the third power, equals. And my calculator answer is this. And you should get that too. As I said, there is no units, so now we have to think, is this given with the proper number of significant figures? And we have, how many sig figs in O2? Can you answer by chat? You tell me 2, 3, 1. Yeah. Yes, the two digits I'm highlighting here are the two significant figures. And what about this number? How many sig figs there? Yeah, the same. So we need to keep two sig figs because we have two sig figs in 0.60 and we have two sig figs in 0.020. So two sig figs means we keep the 4, the 5. What comes after the 5 is a 0. And so it just stays like that. We already have two sig figs there, so it's going to stay like this. Now let's write it in scientific notation to practice. So you can use your calculator by doing the second function, drg, if you have the TI30X2S. Change floating point to scientific, enter, and you have the expression in scientific notation. Um, and that's 10 to the fourth, but you can also find it mentally, right? You can see that here, the decimal point is supposed to be here after the last 0 to the right. So let's see how many steps we need to do to get a number between 1 and 10. 1, 2, 3, 4. 4 steps to go between 4 and 5 and get a number between 1 and 10. And because it's 45,000, it's a large number, so the exponent is positive. Okay. So there is another question. Does the equilibrium mixture contains mostly reactant, mostly product, or both reactant and product? Because the reason why we calculate this equilibrium constant, it's because it has a meaning, right? And we've learned that, or yeah, maybe you have started to learn that when it's a large value like that. So can you tell me, does the equilibrium contains mostly reactant? So say reactant by chat. If you think it's mostly product, say product. Or if you think it's both, say both. So given that large value for K, you can tell how the equilibrium is, driven. Is it favoring product, reactant, or both? So when the value of K is very large, so let me say in there that it's, very large, so much greater than 1, right? If it's much greater than 1, if you think about the formula, that it's product over reactant, if this is much greater than 1, and if you multiply both sides, so both sides by reactant, so multiply by reactant, and you will have only a product here on the left, and on that side you will have 1 times reactant. So reactant here will have a much smaller concentration than the product. Right, and so this tells you mathematically that the concentration of product is much greater than the concentration of reactant when you have a K value that is very large. And if you look at this here, K value very large tells you that the numerator should be very large compared to the denominator. So you have much more product than reactant. That's what it means. And so K is a lot greater than 1. So the equilibrium favors the product. Okay, there's another way to check that, that you can verify that this conclusion is true. It's by looking at the concentration at equilibrium. If you look at those concentration at equilibriums, so O2 is a reactant, and SO2 is a product. And you can see that the concentration of SO2 at equilibrium is 0.60 molar, which is greater than the concentration of O2, which is here a reactant, and it's 0.020 molar. So let me do this. Yeah, it's 30 times greater, right? The concentration of SO2 here is 30 times more than the concentration of O2. So, and SO2 is a product, so that means the equilibrium favors the product. So that's another way to verify what you're saying here from the K value. Okay, so so the equilibrium favors the product, as we can see from the equilibrium concentrations. And I could just add those. Okay, so I hope this is clear. So if you have a K value that is much smaller than 1, then it's the reverse. So much smaller than 1 means your product are smaller than your reactant, right? For a ratio to be much smaller than 1, that means you have a small numerator and a very large denominator. And so that tells you the reactant will be much more abundant than the product. And so a small K value would favor the reactants. And we say we have both reactant and product when the value is close to 1. And here, be aware that close to 1 doesn't mean, you know, 1.5 or 0.5. It really means to go from 0.01 to 100, right? It's really the range when we say close to 1. Oh, so, okay. Let me say that just because I think it's an important reminder. Means close to 1. Oh, that's strange. It's making a... Okay. Okay. Do you have questions on this or? Okay, so now for each of the following changes at equilibrium, indicate whether the equilibrium shifts to the right, to the left, or does not change. So you have this equilibrium here because we have a double arrow that indicates an equilibrium. The reactant here is NOBr, a gas. The products are NO and Br2. And maybe you've seen that sometimes, but here it's adding the enthalpy of, or the enthalpy change or the heat of reaction, and it's positive 340 kilojoules that is added on the product side. So it's like part of the equation here. Sometimes it's written, to the side, but in this way, it's written within the equation. It says when you are going forward, so from left to right, you will have this amount of energy added on the product side. So tell me, what does it mean? Is this equation or chemical reaction exothermic or endothermic when you are having this amount of energy produced when the reaction goes forward? So is the forward reaction exothermic or endothermic? Yeah. Yes. So when the reaction goes forward, uh, from left to right, you produce 340 kilojoules. And so that means the forward reaction is exothermic because you're releasing heat to the outside. So here produce that are released, that are released to the outside. So that's how you should interpret the fact that there is plus this amount of energy on the right side. It means it's exothermic this way, going to the right. You're producing this amount of heat and it's released to the outside. And so that means the forward reaction is exothermic. So then thinking about the rate of reaction, what happens when you are removing some NOBr? So tell me, what happens to the equilibrium? Does it shifts to the left, shifts to the right, or does not change? So you can answer by saying left or right, or no change. So when you are removing some NOBr, so this is all about Le Chatelier's principle. I don't know if you have studied that far in the chapter 6, but Le Chatelier's principle. So it bears the name of a scientist, a French scientist, Le Chatelier. And he found that whenever you are disturbing an equilibrium, the change you are doing to the equilibrium, so Le Chatelier's principle says that the equilibrium will try to counteract that change and to, eliminate it. So it will try to um, uh, come back to equilibrium and counteract that change. So if you're removing NOBr, and NOBr is a reactant here. So if you're removing it, what will happen to the equilibrium if it wants to counteract the fact that you're removing NOBr, what it should do to go back to equilibrium? So this will favor the So when you are removing a reactant, here you're removing an OBR. So you're depleting the side of the reactant. And so the equilibrium will try to replenish that side. And so for the reactant to, bring back some NOBR because you're removing it, so it tries to bring back an OBR, that means it will shift the equilibrium to the left. So the equilibrium will shift to the left to try to um, it will try to, bring back some NOBR, and for this it needs to favor the reverse reaction. Does it make sense, or? So let's look at the second example. When you are decreasing the temperature of this reaction, so it's an equilibrium, which means we don't know the K value, so we can suppose that both reactant and product are present at equilibrium, right? And so here we are decreasing the temperature. So decreasing the temperature, you need to see it like you're removing some thermal energy, right? Removing thermal energy. Thermal energy is like heat, so you're removing heat. And remember that the kilojoules here are representing heat. So you're removing heat, and the equilibrium, when it goes to the right, it will add heat, right? So if you're decreasing the temperature, removing heat, the equilibrium will try to, uh, add heat because you're removing it. So it will try to add. So let me write it so that my words are understood. So the equilibrium will try to add heat. And let me explain here first. So the temperature, decreasing the temperature means removing, removing heat or slash thermal energy. So decreasing the temperature means you are removing heat or thermal energy. Le Chatelier's principle says that when you are doing a change to an equilibrium, then the equilibrium will try to do the opposite, to try to counteract the change and bring back the equilibrium. So it will try to do the opposite. So the equilibrium will try to add heat because you're removing heat by decreasing the temperature. It will try to add heat, and and for this it will have to go by moving the equilibrium to the right, because we see that when you are going to the right, it's adding kilojoules here, right? So this will help bring back some heat. So by moving the equilibrium to the right, because this is the exothermic reaction, because let me say that better, because the forward reaction is the exothermic reaction, and it will add heat, 340 kilojoules per mole that react. So Is this one making sense? It's maybe the hard. So when you are decreasing the temperature, you're removing heat. So the Le Chatelier's principle says that the equilibrium will try to add heat to compensate for the loss of heat. And so to add heat, you see that you need to go to the right forward because this will add this amount of 340 kilojoules when you go to the right. Because if you were going in the reverse direction, if you go from right to left, you see that you will use those 340 kilojoules to go to the reactant side, and you don't want to, use even more heat, which would decrease even more the temperature. So Le Chatelier's principle says, equilibrium will always try to do the opposite of what the change is doing. So let's look at okay, let's look at another example. We are adding some NO to the reaction vessel. So we have this mixture here of reactant and product, and we are adding NO. And NO here is among the products. So you're adding more of this. You have it, and you're pushing, it's a gas, so you're pushing more NO gas into the reaction vessel. So what do you think the equilibrium will do? Yeah. So adding NO, adding NO is adding a product. Is adding a product. So Le Chatelier's principle says the equilibrium. So Le Chatelier's principle says the equilibrium will try to. So you're adding too much product, so it will try to consume the products. To remove that excess of NO that you're adding. So it will try to consume the product. And so for this, the equilibrium has to move to the left to consume the product and make more reactants, from the products. So use those products and make more reactant, to consume the extra NO that you're adding to it. That's how you want to see it. Or it tries to do the opposite of what the change brings. So whenever you're, adding a product, so you're feeding product, so that will push the equilibrium to the left. It will try to consume that product, and that will push the equilibrium to the left. If instead you are removing, let's say you are removing Br2, and I could put that as an example. So if we are removing Br2 as it's being produced, you're removing it from the reaction vessel. If you are removing Br2 as it is produced, then the equilibrium will try to replenish that because you're removing it, so it will try to make more. So removing Br2, 2 means So removing Br2 means you are removing a product as it is being made. So the Chatelier's principle says that the equilibrium will try to replenish, to make more, make more of the product to compensate for the loss of Br2. Make more of the product to compensate for the loss of Br2. So the equilibrium will shift to the right to make more product, because you are taking it away each time it's making some, so it will make more to try to have more product. So it's always doing the opposite of what the change is doing. And we saw that, when you remove a reactant, it moves the equilibrium to the left, because the equilibrium tries to, bring back some reactant. But if you're adding more NOBr, if you're putting much more here, increasing the concentration, then this will, favor the forward reaction. This will, the equilibrium will say, okay, I can use that and consume it because there is too much. So if you bring too much reactant, then it will move the reaction forward, and it will consume that reactant to make product. So let's look at that last example of adding heat. So if we are adding heat, so you need to understand what this means. It means you are bringing energy. It's like increasing temperature. So you're adding heat. And so the equilibrium, so Le Chatelier says that the equilibrium will try to remove that heat or consume it, consume it, use it. So how can we consume and remove the heat? Which way should we go so that we use the heat that is added? So tell me, yeah. Yes. Right? To use the heat, you need to go in the direction that, will use the heat. And here it's going to the left. When you're going to the left, you're using the 340 kilojoules, and they are being used because they are necessary. It's an endothermic reaction when you go in the reverse reaction. So let's say that the reverse reaction is endothermic and will use the heat. So the equilibrium will shift to the left and do that endothermic reaction. We shift to the left to use the heat